Hi everyone, welcome to another Select seminar. Today we have Alex Kissinger, who will be talking about, a paper together with me. It's Scalable spider nest, or how to graphically grok transversal non-Clifford gates. Please, Alex.
Okay, thanks, John. So this is a extended slash decompressed version of the talk that I gave in Buenos Aires this year. So this is a 1 hour version of that 30-minute talk that really should have been a 1 hour talk in the first place. Um, a lot of this stuff, so it's in a paper by the same title, Scalable Spider Nest, or How to Graphically Grok Transversal Non-Clifford Gates. People often ask me what grok means. It means to understand something in a deep and fundamental way. It's from this book called Stranger in a Strange Land. So that's just a little side note. A lot of this stuff is also laid out in quite some detail in our book. So if you haven't grabbed the book yet, here's where you can get it. A lot of what I'm going to talk about today is in chapter 13, which is the error correction fault tolerance chapter of this book. Okay, so I'll just kind of motivate where we're going and explain some basics before I get into what I'm actually trying to accomplish, what are transversal gates and spider nests and all this stuff. Okay, so most people know what ZX diagrams are. These are the language of the ZX calculus. They're made of spiders. And the most general ZX diagrams are made out of spiders with arbitrary parameters. Okay, so I can put any real number here, and that sets the relative phase between these two terms. And we love these, full-powered ZX diagrams because they can represent any linear map, so they're fully universal. And they readily encode universal gate sets. So for instance, this is a universal, this is the Clifford plus phase set of gates. I can do arbitrary phase gates. I can do square root of x, and I can do C naught. So from these, I can build anything. And it's complete for circuit equality with only something like 9 rules. But there's a catch, which is that if we work with full powered ZX diagrams, this can be exponentially hard. Okay, so the only general purpose way, for instance, I can decide equality of two universal ZX diagrams is I can reduce both of them to some exponentially big normal form, which is basically the same size as the matrix that they represent. And then this thing is unique, and I can compare these things. But that's not very useful in practice for any reasonable number of qubits. So normally we think about fragments of ZX. So a couple of relevant fragments are the Clifford fragment. So this is where we reduce all of the phase parameters to be pi by 2s, integer multiples, pi by 2. And then there's this, which I'm showing here, is a complete set of equations for the Clifford ZX diagrams. And a lot of the things that we know how to do for universal diagrams, we actually know how to do efficiently for Clifford diagrams. So we can efficiently synthesize, say, Clifford circuits out of unitary Clifford ZX diagrams. We can do efficient equality checking. We can do strong classical simulation, compute arbitrary marginal probabilities, that sort of thing. I think a useful way to conceptualize Clifford ZX is that this is the graphical version of stabilizer theory and of stabilizer codes. So this is where 99.9% of quantum error correcting codes are stabilizer codes, which are normally defined in terms of stabilizer subgroups and things. Clifford ZX is basically the graphical version of that theory, of that framework. So even smaller than the Clifford ZX fragment is the phase-free fragment. So this is where we actually set all of the phases equal to 0 in our ZX diagrams. Okay, so a spider with a 0 phase is just written as an unlabeled spider. Here we have 1, 2, 3, 4, 5 rules. And this is actually a complete set of equations for the phase-free fragment. Okay, so I say it's a complete set of equations for qubit phase-free quantum computing. I guess really what that means is that I can decide arbitrary equations between phase-free ZX diagrams, including, for example, C-naught circuits. And And yeah, again, like the Clifford case, we have efficient synthesis, equality check, and classical simulation. A useful way to think about this fragment is this is the graphical version of doing linear algebra over the field with two elements, so F2 linear algebra. Or you can think of it as graphical CSS codes. So CSS codes are Calderbank-Shor-Steen codes. These are a particular kind of stabilizer code in quantum error correction, which has this nice structure, which is quite related to F2 linear algebra, and therefore it's quite related to classical error correction. Okay, so phase-free ZX diagrams are made of spiders where the phase is set to 0. Okay, so those are these two spiders. But in the phase-free case, it's actually often quite useful to think of the X spider. So this is the Z spider. It's quite useful to think of the, oh yeah, you can't see where I'm pointing. But in the second line, it's quite useful to think of the X spider in terms of the computational basis as a kind of a generalized XOR operation. Okay, so when I can write this spider up to normalization as a sum over all the parity 0 bit strings. Okay, here it's got some inputs and some outputs, so I put some of the bits here in the ket, and I put some of the outputs here in the bra. But you can just think that this is a generalization of an XOR operation. So if I specialize this to where I had 2 inputs and 1 output, this would actually just be the definition of the XOR map on your basis states. Okay, but the X spider is like a many-legged XOR. And one of the nice things about phase-free ZX diagrams is it's very easy to explain how to reduce these things to a canonical form. So here's a little simplification strategy. You can quite easily code this up in 5 or 6 lines of Python code using the physics library, for instance. And it goes like this. So I apply spider fusion and the identity rule as much as possible. Okay, so at that point, then I will end up with no spiders of the same color adjacent to each other, and I'll end up with no 2-legged spiders because they'll all be turned into wires. And then I apply this rule, the strong complementarity rule, once in a position where the Z spider, or the green spider, is not an input, and the red spider is not an output. And then I repeat. Okay, so to understand what's going on with this step 2, you can think about what this canonical form is trying to accomplish. We're trying to get all of the Z spiders on the input. We're trying to get all the red spiders on the output. Okay, so what this simplification is saying is anytime I have a pair of spiders which are not in that configuration, just apply strong complementarity, and we'll actually move closer to a situation where I'm in that configuration. Okay, so this terminates in polytime to a normal form which looks like this. So it's got Z spiders all on the inputs, it's got X spiders all on the outputs, and in general, so in cases where this thing is not a unitary, I will end up with some extra interior X and Z spiders. So I'll have some interior X spiders which are just connected to some inputs. I'll have some interior Z spiders which are just connected to some outputs. In the book, we call this a generalized parity form. Okay, in the special case where we have unitaries, actually these interior nodes go away. So you can show that if this overall map happens to be a unitary map, then J has to be K has to be 0. Okay, so unitaries, of course, have the same number of inputs and outputs. And furthermore, you can show that they don't have any of these interior spiders. Okay, so in the unitary case, it looks like this. And this is what we call a parity normal form. So not a generalized parity form, but a parity form. Call it that. Well, if you think about a CNOT circuit, okay, what is this classical bit string in? And it outputs some XORs, or what you could call parities of some of those bits. Right, so here, let me just write it into ZX notation. So C0 gate looks like this in ZX notation. if I apply my simplification strategy, I get to this parity normal form. Well, it says that what this circuit accomplishes is I input some bit strings, or I input some bits here, and what comes out is some XORs of those bits. And now the XORs of which bit can be read off just from the connectivity of this parity normal form. Okay, so you can see, for instance, on the first output qubit, it's connected to X0, X2, and X3. And this is saying that, in fact, the output of this first qubit should be the XOR of X0, X2, and X3, and so on for the rest of these. So you can see that essentially the parity normal form is just this bi-adjacency matrix, which is telling me which bits to take XORs of to form outputs. Okay, and this is something you get to graphically just by applying the simplification strategy. Okay, so here I can write this bi-adjacency matrix L as a Boolean matrix. And in fact, you can see that the overall action of this unitary is really just to take in a bit string and apply this Boolean matrix modulo 2 to that bit string. Okay, so that's a very compact way I can write what a C0 circuit does. Okay, so that's how it works in the unitary case. The isometry case is not very far off from that. So this is obviously a bit weaker. So an isometry says that its adjoint is actually just a one-sided inverse. This implies that I have to have fewer inputs than outputs. And still that these interior X spiders should not be there. Okay, so J equals 0 in this diagram. So I end up with something that looks like this. Okay, but unlike in the unitary case, I am actually allowed to have some of these interior Z spiders. Okay, so K is allowed to be non-zero. Okay, so what do these things correspond to? Well, again, I can look at this thing in terms of taking some XORs of bits. Okay, so I have these two input bits, X0 and X1, but I also have these kind of interior bits. Okay, I wrote them in a different color to tell you that this is a different kind of thing going on. But you can see that I can still think of my outputs as XORs of now these two different kinds of variables. Okay, so I have these input variables, and I also have these inside variables, Y0 and Y1. Okay, so what's the difference in the blue ones and the red ones here? Well, the blue ones are actually the input to my isometry. So again, I put in a computational basis state into some isometry V. But the red ones are actually just getting summed over. Okay, so I can think I have this matrix L, which captures the connectivity between my inputs and my outputs. But I have a second matrix S, which captures the connectivity from these interior things to my outputs. And what does the action of this overall isometry do? Well, it takes X to L times X plus S times Y. But the difference is here I sum over all the Y. Okay, so you could imagine looking at this picture at the top. I'm sorry, I can't really point at things, but you could imagine if I have these two interior Z spiders, I could sort of unfuse a green state, a Z state, onto an input. And I could think of that as an input that's being summed over rather than an input that's left open. Okay, so that might be a useful way for you to think about these things. But anyway, this is just the direct way I can write down the action of this isometry once I have this normal form. But importantly, it's given now in terms of a pair of matrices. I've somewhat suggestively called these matrices L for logical and S for stabiliser. So that's gonna come up again. Okay, but before I get to there, I'm going to show you scalable notation. Okay, so this is quite useful, especially for these phase-free diagrams or things which have large phase-free components. So this is a notation where we are allowed to have not just single qubit wires, but also have registers of qubits. So I can rewrite this thing. So this is a parity normal form. I can rewrite this into scalable notation as something that looks like this. Okay, so now what this is telling me is I have a register of 4 qubits connected to a register of 3 qubits. And in fact, the way that they're related to each other is via this adjacency matrix. Okay, so now I've kind of abstracted over this connectivity and I've hidden that complexity into this matrix L. Okay, so for just a single thing, this is, not that interesting, but as we'll see, you can start to mix the graphical notation with this parity matrix notation, and you can get some quite interesting kinds of calculations going. Okay, so scalable notation, I'll just tell you a little bit about how this notation works if you haven't seen it before. So a fat wire labeled with an N means a register of N qubits. Fat spiders or bold spiders just mean N spiders parallel composed with each other. Okay, so here I'm taking my first wire of this register to the first spider and the second wire to the second spider and so on, all the way up to N spiders, and same with the outputs. And I can do this for either color. And most importantly, I have this new arrow thing. Okay, so the arrow says make a biadjacency matrix with Z spiders on my input, X spiders on my output, and connect them according to this binary matrix A. Okay, so putting Z on the input and X on the output is just a convention. So it's important that we keep the input and the output separated from each other. But of course, we could have taken the opposite convention because everything's color symmetric. But we'll stick to this one. Okay, this satisfies some nice rules. So for instance, if I have a pair of arrows and I compose them like that, the matrices just multiply. I can push an arrow forward through a green spider, or I can pull it backwards through a red spider. Okay, so you notice that there's some asymmetry in these rules, and that the arrowhead has to be pointed toward green, but it has to be coming out of red to do this kind of copy type rule. Okay, so if we took the other convention for our arrows, then these two rules would have been flipped. And we can also represent block matrices. So if I have a register of N qubits, I can sort of split that up into 2 smaller registers. And if I write a block matrix like this, according to that partition, then you can sort of see them appearing A, B, C, D like this. Okay, so here's the first row, I guess, are the 2 things coming into the first red dot, and here's the second row, the 2 things coming into the second red dot. Okay, and in fact, you can even take this last equation to be the definition of the scalable notation, because you can apply it recursively until I get all the way down to the bottom. Okay, so that was just really fixing some notation. Let me talk a little bit about quantum error correction now.
I have a question.
Yes, go ahead.
So could you go back to previous? So do you have any meaning if you want to flip this shape and perform a reflection about it of the y-axis? Like, does that correspond to the inverse or transpose of the matrix?
So if I write an arrow going in the other direction, then that will correspond to the transpose of the qubit matrix. So you have to be a little bit careful here because we have 2 kinds of matrices going on, right? We have this exponentially big matrix, which is connecting qubits to qubits. We also have this small Boolean matrix, which is telling me about the connectivity. So if I flip the arrow around, this is like the normal transpose. Like if I transpose a big quantum unitary, then that's the same as flipping the arrow around. The other fact that's useful is if I point the arrow backwards and I transpose the label on the arrow, this is the same as flipping the colors.
Sorry, how do you transpose elements?
Yeah, let's see if it's I wonder if there's a useful way for me to write here. So if I have an arrow like this and I label it by a matrix A, then that's going to be a bunch of Z dots connected to a bunch of X dots according to A. So here this connectivity will be given by A. But a useful thing which comes up a lot in thinking about these CSS codes is that I might want the color reverse of this picture on the right-hand side. Okay, so I may want the exact same connectivity, but I want all of these to be red dots and all of these to be green dots. And the way that that's represented is I put an arrow going the other direction, but I label that arrow with A transpose. So then essentially I will get the green dots on that side, I'll get the red dots on this side, and the connectivity here will be given by A transpose, which is the same as having the connectivity of A, but sort of going in the other direction. So if that makes sense. Okay. Another way to remember this is if I have a H gate, where here I mean n copies of an H gate. So this is a register on n qubits, and I push it through an A, then it reverses the direction of the arrow and makes it A transpose when it goes through. Okay, so this is a rule that always holds in Scalable. And that's the way that you can remember how to do color reverses here.
Thank you.
Okay, so make sure that's showing up right. Yeah. Quantum error correction. A way that I like to think about this is that you can imagine this kind of encoder map. So this isn't really something that's real. This isn't something that you necessarily do on your quantum computer, but you can imagine that I'm embedding some K logical qubits into a bigger space of n physical qubits. Okay, so I can just kind of remember what this encoder does is it sort of remembers how K qubits are mapped into this bigger space. Okay, this bigger space has some redundancy in it, which I can then use to measure quantum parity checks, essentially to do some quantum error correction. Okay, so this encoder E, or often just the image of E, is called a quantum error correcting code. And a stabilizer code is the special case where E is a Clifford ZX diagram. Okay, or you could just say that there exists some Clifford ZX diagram, and the image of E is called a stabilizer code. Now, a CSS code is even more specialized than that, and this is where E is a phase-free ZX diagram. Okay, so both of these things have a definition in the literature, and that definition is equivalent to this fact that I have an encoder and I just write it as a ZX diagram in one of these fragments. Okay, so here's a isometry. So remember from before that I said that isometries take this particular form if I reduce them to normal form. And this is also, now by the definition on the previous slide, this is going to be a CSS code. Okay, this CSS code is defined by two things, by this matrix L, which is the logical, call this the logical matrix, and this matrix S, which in fact here only has one column in it, which is called the stabilizers. Okay, so this is a particular code. This is what's called the 422 error detection code. So it's one of the smallest codes that you can come up with. Okay, so if you are used to thinking about stabilizers and logical operators, you can translate between this graphical picture of the encoder and this more traditional way of thinking about it by just taking the columns of this matrix to be the X logical operators, and taking the columns of that matrix the columns of L to be the X logical operators and the columns of S to be the X stabilizers. Okay, so a nice thing about CSS codes is they are totally fixed by just one kind of operators. So you always have these kind of all X operators and these all Z operators. But in fact, I only have to give you one family, and then the other family is uniquely fixed up to a choice of generators. So here, this totally defines the code, and here's the X operators associated to it. But in fact, this diagram has an equivalent form. So you notice here I wrote it in this generalized parity form where I've got Z's on the inputs and X's on the outputs. There's an equivalent form where I've got X's on the inputs and Z's on the outputs. And in fact, this will give you the Z logical operators and the Z stabilizers. Okay, so what I'm saying here is that there's this graphical way that I can write down this encoder map of a CSS code. And in fact, there's really a direct connection between how this encoder looks graphically and then also its stabilizers in the sort of more traditional way of talking about this code.
Quick question here.
Yeah.
So this way is convenient for writing it in the Scalable ZX form. But would there also be a convenient way of writing it for the Scalable ZX form for non-CSS codes, i.e. ones that have mixed stabilizers of Z and X?
When you have mixed stabilizers, I guess there's not a unique canonical answer. So there are normal forms for ZX diagrams. But it's a bit less obvious. There's a few different ways that I could represent a generic stabilizer code.
Like the 5-qubit code, for example.
Yeah, so one thing you can do is you can write that as a CSS code followed by a diagonal unitary.
Mm-hmm.
So this is possible for any CSS code. I can write it as a or for any stabilizer code. I can write it first as a CSS part and then a diagonal unitary. Both of these parts, I can write them in scalable notation. So essentially you get the data kind of factoring into three pieces. You get the kind of pure X logicals, the pure X stabilizers, and then this diagonal unitary, which kind of converts. Yeah, maybe I should say the pure Z logicals, pure Z stabilizers, and a diagonal unitary, which sort of generates your mixed stabilizer generators. But it's a bit of an open question because there's also other normal forms that have other properties. So and it's not real clear yet what's kind of the most convenient one for working with. Yeah, so here this is it written kind of unfolded. I can also, if I have a CSS code, I can write it in the stabilizer notation pretty compactly this way. Okay, so here I've just got my logical matrix and my stabilizer matrix written as arrows in this diagram. And the difference between the two is the L matrix is connected to the inputs and the S matrix is connected to a bunch of green dots. Okay, so here I can write the encoder for a generic CSS code this way. Okay. So why is it useful to have a graphical picture of the encoder? Well, one thing that it's useful for is for reasoning about fault-tolerant computations. Okay, so normally we don't want to just use error-correcting codes as memories. We actually want to do computation on the encoded qubits. Okay, and one naive way to do that is we could just decode all the qubits, do the computation, and re-encode it. But this isn't going to work because if errors happen in the process of doing that, then we've lost fault tolerance, so we've lost the kind of benefits of doing this in an error-correcting code. So something you can do instead is you can think, well, maybe there's some logical operation, little f, which I want to do to my logical qubits. But I can do that on the encoded physical qubits if I find some physical operation, big F, which satisfies this equation. Okay, so we sometimes call this the pushing through the encoder equation. It's kind of like this big F is the thing happening on the physical side, which corresponds to this little f on the logical side. And then often, so for example, with unitaries or more general kinds of maps, we might want this thing to be transversal. Okay, so for a single code block, that means that we actually want the thing to factorize a single qubit gates or operations. For multiple code blocks, we actually want to say that each of our operations only involves a single qubit from each code block. Okay, so in general, this is going to stop these operations from spreading an error. So if we have an error happening on a single physical qubit, it's not going to spread it onto multiple physical qubits. Okay, so finding transversal implementations of logical gates is an interesting and important thing to do for FTQC. Okay, so in general, it's easy to classify all the transversal Clifford gates. You can do this in a number of ways. One way is just by reasoning about what they do to the stabilizers. So any Clifford gate which preserves the stabilizers of a stabilizer code is going to act on the logical space. And then you can just look at the local Clifford gates to find the transversal ones. But transversal non-Clifford gates are less well understood. At least in the fully general case, this is less well understood. However, the diagonal non-Cliffords actually do have some nice structure, and there are many things known about which of these are transversal. Okay, so the diagonal non-Clifford gates are actually all generated by these things, which written in ZX notation are called phase gadgets. Okay, so this is a generating set which actually generates all the diagonal unitaries. And the convenient thing about taking this set of generators is if I take a fixed angle on these phase gadgets, I can actually fix my level of the Clifford hierarchy. Okay, so the Clifford hierarchy is this growing sort of set of families of gates, which have some nice structure with respect to the Cliffords. The one that's considered probably the most is what's called the third level of the Clifford hierarchy. So Cliffords themselves are at the second level. So one level up from that, the third level contains the T gate and the control Z gate, which written in terms of phase gadgets look like these two pictures. Okay, so this is an interesting thing to consider, because if we throw either of these in with the Cliffords, then we get a universal set of gates. Okay, so in ZX land, we've been thinking about phase gadgets for a while. So one of the first things that we were using them for was doing optimization, for instance, to reduce the number of T gates in a circuit, where the rule that really does the work for you is this thing called gadget fusion. Okay, so this says if I have a pair of phase gadgets and they act on the exact same set of qubits, then I can just add their phases together. Okay, so the way that this ends up working for you in circuit optimization is you can find T gates, which even if they're far from each other, if once I do this ZX reduction, they end up acting on the same set of qubits, then I can fuse their phases. So say maybe I have two pi/4 phases, they add to become a pi/2 phase, which then corresponds to a Clifford operation. So for example, here's a C0 plus phase circuit. I can do something like this, where I unfuse all of these non-Clifford phases. I can reduce it to a normal form. So here I've really treated these non-Clifford phases as outputs, as well as my actual outputs, and then I just reduce to a phase-free normal form. And then I can do some gadget fusion, right? And then I've ended up getting rid of one of these non-Clifford phases here. And I can then re-extract a circuit, or you can do this thing called phase teleportation to really just move the phases around in the original circuit. Okay, so there's many things you can do with phase gadgets in circuit optimization. But in fact, something that we showed last year is that if I want to consider general alphas, so arbitrary parameters, this is pretty much the whole story. I mean, so gadget fusion is basically the only optimization that works for arbitrary values of alpha. Okay, so this whole kind of continuous family of gates. However, as soon as you restrict to specific angles, you get lots more rules starting to show up. And you get non-trivial, non-Clifford rules appearing. So for instance, if I have alpha equals pi by 4, you get this funky looking rule. Okay, so this looks like a lot is going on here. But actually, all that has happened on this left-hand side is I've taken a phase gadget and I've hooked it to every subset of these 4 nodes. In fact, it's every non-empty subset. So here I've got 15 non-empty subsets of these 4 nodes. And if I hook a pi by 4 phase gadget to all of them, it turns out they all cancel each other out and give me the identity. Okay, so this is a non-trivial rule which doesn't follow from the rules of the Clifford ZX-calculus. Of course, it follows from the universal set of rules because of completeness. Okay, so these non-trivial rules are called spider nest identities. Okay, so where this project / paper kind of kicked off was we were thinking about a nice way to try to classify all of these non-trivial rules and work with them in a more effective way. Okay. And it turns out that using Scalable ZX, we have a quite a nice way of thinking about this whole family of rules. Okay, and in fact, they all take the following form. So they're all of the form of some bunch of phase gadgets. Okay, so the way that I can write a whole bunch of phase gadgets is actually just, I put a parity matrix here. Remember, this is a bunch of green dots connected to a bunch of red dots. And then I connect all of those red dots to a pi by 4 spider. Okay, so now M is just capturing the fact that I have a whole bunch of these pi by 4 phase gadgets. And all the spider nest identities are of this form, where I have some M, some bunch of phase gadgets described by M equals the identity. Okay, so this doesn't hold for any matrix M, but this holds whenever the matrix satisfies this condition of being what's called triorthogonal. Okay, so what is triorthogonal? Well, it's this condition. Okay, it's a little bit technical, but it's a pretty easy thing to check, right? So if I could write up some code to check this quite quickly. It says that each of my rows have a Hamming weight of 0 mod 8. Each of my dot products of a pair of rows, or element-wise products of a let's call this dot products of a pair of rows are 0 mod 4. And this kind of threefold dot product of all triples of rows are 0 mod 2. Okay, so it's called triorthogonality, or you might, we've called this strongly triorthogonal, but yeah, the literature is a little all over the place on what to call this. Okay, so that's kind of the general thing, this rule. And something that's kind of nice is we can actually prove all of these identities graphically just using the Clifford ZX-calculus and one additional rule. Okay, so what's the idea here of showing this? Well, first of all, we can define a inductive family of diagrams here. So we have these diagrams called S sub something. Okay, so S sub 0 is just a single pi by 4. And then S sub n is defined in terms of S sub n minus 1 in this kind of way. And then we just add one additional rule to our system. Okay, so we say actually that S sub 4 disconnects like this. Okay, so this I could totally unfold this left-hand side. It's, you know, it's a relatively complicated diagram involving a bunch of pi by 4s ultimately, and it just says that these all disconnect. And then we can prove the theorem. So the Clifford ZX-calculus plus this one additional rule is what we call diagonally complete for Clifford plus T ZX diagrams. So that means any ZX diagram whose phases are multiples of pi by 2. For any such ZX diagram, we can prove any true equation of the following form. Okay, so where I've got some collection of gadgets equals some other collection of gadgets. This is provable using just S4 and the Clifford rules. Okay, so that's the statement. Any questions about the statement of the theorem, or is that kind of clear?
Do we assume anything about MN?
Here, no. So this is just saying it's well, I say any true equation. So I mean, if the matrix on the left-hand side equals the matrix on the right-hand side, then it's going to be provable. Okay, so certainly for arbitrary m and n, these things could be just describing different unitaries. But if they describe the same unitary, then they can be transformed into each other using just the Clifford rules and S4.
So N and N do not have to be triorthogonal.
They don't have to be triorthogonal themselves, no.
Okay, thank you.
Okay, so I'll give a sketch of how this works. So we use a bit of extra machinery, but I won't go into the details here. So first of all, just using this inductive definition, it's pretty easy to immediately see that S4 disconnects, certainly, but also Sn disconnects for every n greater than 4. Okay, so why is that? Well, if I look at S5, for instance, then it's got 2 S4s in here. Each of those will disconnect. Oh yeah, you can't see what I'm pointing at, right? But if you look at the top right, if I make Sn to be S5, then it's got 2 copies of S4 in it. Each of those would disconnect. Therefore, S5 would disconnect. And then you can argue inductively that all of the ones bigger than S4 disconnect. But then using that fact, you can show that this forms an infinite generating set for all the spider nest rules up to Clifford's. Okay, and this is where I said we use some machinery that I won't really talk about. This has to do with the fact that there's an equivalence between triorthogonality and low degree polynomials / Reed-Muller codes. Okay, so this is using some sort of known things about the structure of triorthogonal matrices and the fact that these things correspond to low degree polynomials in a certain sense. Okay, but yeah, I'll maybe jump over that and say a bit about transversal gates. Okay, so what does this really tell us about transversal diagonal gates? Okay, so now I'm trying to find things pi over 4 phase gadgets. So imagine I've got a little f, which is described by pi over 4 phase gadgets. I want to know which of those are representable transversally or implementable transversally. Okay, so if I have this equation and f is unitary, then I can just put it on the other side. So really, I'm looking for things which satisfy this property with my encoder. Okay, so if I'm interested in pi over 4 phase gadgets, that's saying that I'm looking for some capital H and some P where P is transversal. Okay, so that means I think that each of its rows is a unit vector. Okay, that means it only involves a single qubit. Yeah, so each of the rows of PI is going to be have a single 1 in it, which satisfies this equation. Okay, so then we can do some work with the scalable notation to see what satisfying this notation or satisfying this equation means for a CSS code. Okay, so here I have a CSS code described by a pair of matrices, L and S. And I want to know what sorts of H's and P's satisfy this equation. So I can push P to the left. Okay, so here I'm using ZX-calculus. That first step is just strong complementarity. And then I can use some scalable rules. And I just keep pushing this thing to the left until I get to something like this. Okay, so now this thing, you can see you can see the two green dots on the bottom connected via 4 arrows to the 2 red dots on the top. This is the form of a block matrix. And that block matrix is this D sub m I've written. Okay, so D sub m is the diagonal unitary corresponding to this matrix M, which is a block matrix. Okay, so this says that P is a transversal implementation of H if and only if this equation above is satisfied, which is true if and only if M is triorthogonal. So this unitary dm vanishes if and only if M is triorthogonal. Okay, so you can use that to state this as a theorem. So a CSS code defined by this pair of matrices L and S admits a transversal implementation of a gate D sub H dagger, which is in the 3rd level of the Clifford hierarchy, if and only if there exists a matrix P whose rows have Hamming weight 1 such that the following matrix is triorthogonal. Okay, so this is a bit of a mouthful, but if you look at how this is stated in various places in the literature, this is basically always complicated. Okay, and I think this is one of the simplest ways that you can state this in the kind of full generality for the 3rd level of the Clifford hierarchy, or of the diagonal Clifford hierarchy. Okay, so there's a few pretty well-known examples of this phenomenon in the literature. So one example is if I have the 1513 quantum Reed-Muller code. This is one of the first examples used for magic state distillation. Then I can write it as one of these block matrices M, where the P part, so the physical part, is the identity matrix. Okay, so that means just do a T gate on every single physical qubit. So that's T to the tensor power 15. And then this block right here in the upper left is just a single 1. Okay, so that's just a single T gate. So the logical thing that doing a physical T on everything accomplishes is that it does a T dagger on my logical space. Okay, and normally you can use this fact to do magic state distillation. Here's another example. So this is what's called the smallest interesting color code, sometimes based on this blog by Earl Campbell, or as popularized by this blog by Earl Campbell. And again, you can write down this M matrix. I'm reading the various parts of it. Again, P equals the identity, so that means doing a T gate on every physical qubit. But now I've got a much more interesting H part, which is actually all of the parities on 3 qubits, which is the same as a CCZ. Okay, so this says that doing a T on all of my physical qubits is the same as doing a CCZ on my 3 encoded logical qubits. Okay, so you can read all of this stuff off of this single matrix. Okay, so that might be a good place to stop in case people well, no, let me just conclude and then I can see if people have some more questions. So scalable notation, I would say it tames the complexity of spider nests. So these spider nests can be these big, nasty looking graphical equations. But in fact, the right way to think about these equations is in terms of triorthogonal matrices. And the scalable notation lets me just put a triorthogonal matrix in my diagram. Scalable diagrams represent the Clifford and the non-Clifford parts together, allowing these different structures to interact. So you notice that even if you didn't follow the details of this proof, the kind of dynamics of it was that I was representing my CSS code as a pair of these arrows, which was kind of my Clifford part of the diagram. And I was also representing my phase gadgets using an arrow. And I was letting these two parts of the structure interact with each other. So some kind of interesting open questions here. So one thing that's maybe just kind of a curiosity is that we know that Clifford plus this new S4 rule, remember I said it was diagonally complete. We actually know that it's not complete. Okay, so you can give an incompleteness argument for this. So it'd be interesting to see if there's a route to getting complete Clifford plus T rules using S4, but then I guess maybe something else like supplementarity. Another question is, does this help with searching for new codes, coming up with new distillation protocols, new implementations of fault-tolerant gates? Can we apply this to other kinds of fault-tolerant operations and not just transversal unitaries, but thinking about projective stuff? And also thinking about, recently we've been thinking a lot about things which are not even just stabilizer codes, like Floquet codes, where the stabilizer group is changing all the time. And does this picture, where does this encoder picture live? And can we use scalable notation to our advantage in those kinds of situations? I think is an interesting question as well. And with that, I think that's where I want to finish up. So happy to answer questions.
I have a question. You mentioned that transversal gates are nice, and that is, of course, because if we have sequential gates for making a logical operation, we might leave the code space.
Mm-hmm.
But I think I remember that there cannot be a transversal universal gate set on a QC code, right? So yeah. In that context, do you think that the ZX-calculus can also be reasonably used to try to work on logical operation schemes that do not leave the code space or go to different code spaces, such that we can fault tolerantly do arbitrary quantum computation?
Yeah, so I mean the thing that you mentioned is the Easton-Nil theorem. So there's this no-go that any quantum error correcting code which is non-trivial, so it can detect arbitrary single qubit errors, necessarily does not have a universal set of transversal gates. There's a few ways of getting around this, and I guess the most common way is to think about not just doing everything unitarily, but thinking about incorporating measurement-based protocols, whether that's doing some magic state distillation and then doing state injection, or thinking about codes which are sort of have some kind of dynamical nature, so you actually change which code you're working in, and maybe this has a different set of transversal gates. And things like that. So
because in particular with T gates, right, you can do arbitrary approximation with Clifford plus T. But arbitrary approximation maybe sounds better in theory than in practice if it leads to a very long circuit. And so maybe that is also an issue. Yeah.
Yeah, I mean, this is, at least in the fully fault tolerant regime, I don't think this is such a big issue, because things like the Solovay-Kitaev theorem say that we've got pretty tight bounds on the overhead that we would give, sort of rendering our circuit as Clifford plus T circuits. But Clifford plus T is already ruled out by the Easton-Nil theorem, so you can't even have approximately universal things in a code. So the bigger problem there is that you have you have quite large overheads coming from things like magic state distillation to give you the T gates. Recently, there's been some new ideas that seem to get these kinds of numbers way down. But there's other kinds of trade-offs, like you can't get those as clean as the kind of standard magic state distillation things. I think a place where ZX and this way of thinking about codes could be useful is that we have a bit more freedom in what we consider to be an error correcting code. So for instance, in the recent stuff that I've been working on with Ben Rodatz and Boldy-Poor, so our recent paper about flowcahification, and actually lots of people are working on these kinds of situations where you don't really have a static code, but you think about a circuit with some measurements in it as a code. This could allow more possibilities for fault-tolerant computation, get around the Easton-Nil theorem because the code is changing all the time. But I guess I don't have something real specific to say there. It's just that this is quite a flexible way of thinking about codes and a kind of a nice space for searching for new ideas.
So I have a question. Could you scroll back to the previous slides? In this example, you said, oh, because P is equal to identity, so we know that the non-Clifford gate is implemented transversally. How is this established?
So what this is saying is that if I do H, if I do these gadgets before my encoder, these gadgets described by the H matrix, and I do the gadgets described by the P matrix after my encoder, then that's the same as doing nothing. So imagine now taking these H gadgets over to the other side as the adjoint. Then this is a pushing through the encoder type picture. So it's saying that if I do CCZ on my logical space, that's the same as doing a T gate on every qubit of my physical space.
Oh, because P here is the identity, so it means that every pi over 4 is acting on one wire. So that's why you have the transversal implementation of the CCZ.
Yeah. So you were asking about this P equals I. Yeah. So that means that here I have 8 phase gadgets where the jth phase gadget is acting only on the jth qubit. So that's the same thing as saying I do a T gate on every single one of my qubits.
Right. So if we think about this more generally, if P, instead of being a identity matrix, but it is a sparse matrix, can we interpret it as it is an implementation of some logical gate with low number of supporting qubits?
Yeah. So if you wanted to generalize this a little bit, you could say, well, rather than an identity matrix, let me just allow some repeated rows, or allow some rows to be missing. This is the same as applying a power of T on all of my qubits, where that power could be 0, in which case I'm doing nothing. But you could also think about other things where I would bound the weight of each of the rows. So maybe, each of my gadgets is only affecting at most 2 qubits, right? This is not strictly a transversal thing, but maybe if you only wanted things to be sort of semi-fault tolerant or something like that, that would be an interesting thing to think about.
Yeah, I was asking this because at the end you were saying one of the future direction is the code search. So are you thinking about your now, instead of fixing the code, you're fixing some implementation of a logical gate, and then you will find out what kinds of code would have the desired property such that the logical gate are fault tolerant.
Yeah, so I don't know how to do that, but I think that would be an interesting thing to try. So one thing you can do is if the code is fixed, you can efficiently enumerate all of the logical transversal group for D3 or actually any level of the Clifford hierarchy. So this can be done efficiently. So I can give you the generators for the transversal group, which basically tells you here are all of the D3 gates that I can implement transversally, or here's a generating set for all the D3 gates I can implement transversally, which is just as good, really. That can be done efficiently for a fixed code. But what you said was the opposite thing. So let me fix the thing that I want to do, and let me try to enumerate codes which have that property. I think that's harder because obviously you want codes with some decent amount of code distance. So that's, you're no longer in a space where you're just solving some linear equations. So I think this is going to be hard, but maybe there's some interesting heuristics for doing this.
Thank you.
I have a question. If you can hear me.
Yep.
This is like the question I always ask, but do you know if this generalizes to Q dits? Because like the thing that worries me is this triorthogonality condition, because you have like mod 4, mod 8, mod 2, I think. But it seems like using the scalable notation that everything is very clean compared to before, and maybe you can just like, replace 2 with P or something.
Yeah, I expect this would work for prime dimensions, at least. Where basically you should just go through and replace all the 2's with your dimension as the base. So take mod p, mod p squared, mod p cubed.
Okay, but nothing exists in the literature which like talks about this at all. It's just feels like the right thing, right, to do. I guess it's all qubits, I presume.
Yeah, I mean,
yeah.
Maybe a place to start looking for that. So these triorthogonal matrices are quite related to Reed-Muller codes. So if people have thought about doing Reed-Muller codes not over bits, but over other prime fields, or even over other Galois fields, then you probably would inherit the structure in the same kind of way as this triorthogonality does.
Okay, thanks for the response.
So I have a similar question, but it's quite different direction. So you're characterizing diagonal gates that list on third level of Clifford hierarchy. Is there a possible kind of intuition of characterizing things that do not live in the Clifford hierarchy? For example, for Qtret, there's a gate called metaplatic gate, and it does not live anywhere, but it also have this very nice diagonal properties. I'm not sure if this would kind of connect in some way to the diagrammatic representation of the CSS code.
Yeah, I don't know. So this way of working definitely only works for the Clifford hierarchy. So you have this kind of relationship to triorthogonal matrices for D3. And in fact, you can have L orthogonal matrices for DL. So this works for every level up the Clifford hierarchy. If you go outside, I mean, so you certainly won't have continuous families of transversal gates. So this is one of the things that the Easton-Nil theorem proves, is that to be a transversal gate, it sort of discretizes your space. But I can't offhand think of any reason that they would have to be in the Clifford hierarchy. It's just that we have nice tools for thinking about things in the Clifford hierarchy. But I could be wrong. There could be some reason that sort of forces them to be in there.
So what tool that we saw today is related to the fact that they live in the Clifford hierarchy?
So this tri-orthogonality or L-orthogonality really is something that's special to phase gadgets whose parameter is pi over 2 to the I guess it would be L minus 1 for the Lth level of the Clifford hierarchy.